Thank you. All right, so my name is Amol, and in the next hour or so, we are going to sort of brainstorm on why Scada security is such a uphill battle. I'm director of vulnerability labs at Qualys, which is a vulnerability and compliance management company. So let's get started. Before this talk, I was talking with some folks outside, and incidentally, they knew about Scada systems and should be here in the talk because they said we are going to attend the talk. So my question to them was, what is your expectation from the talk, from generally GrrCON as well as my talk? So some of them were pen testers, and they said, well, we just don't want to see just bullet points. We want to see some actual meat, some code, some packet sniff, something like that. While some of them were more on the management front, and they said, well, that's all good, but we would also like to see or get a general overview of what's happening in the Scada world and how do I protect my critical infrastructure. So I've sort of geared my talk to appease both type of audience. There are a lot of slides, so let's get started. So the agenda for the next hour or so is that we'll go over some Scada basics. Scada is vast and diverse, and what I refer to as Scada may not be something that you would refer to as Scada. So we'll go quickly over some of the Scada basics so that all of us are in the same page. We'll look at threats. So where are these threats? Why do these threats exist? And how can an attacker or a hacker hack into your Scada or critical infrastructure system? We'll look at challenges. So if we know where the threats are, if we know why the threats are, if we know how an attacker can attack us, why don't we protect against it? What are the challenges? We'll go over some recommendations and proposals on securing Scada system. And last but not least, we'll go over a free tool that I have developed. It's called Scada Scan that you could potentially run in your environment to get an idea about your Scada systems. So as you can see, a lot of things to cover in just 1 hour. Let's get started. Also, at any time during the talk, if you have some experiences to share, if you agree or disagree or strongly disagree with something, just give me a shout out and we'll quickly discuss those topics. All right. So it was about 5 years ago when one day my boss comes to my desk and tells me that, hey Amol, do we have vulnerability signatures for Scada systems? Now, to give you a little bit of a background, what my team does is we write signatures to identify vulnerabilities, possible threats, misconfigurations, or any way in which an attacker or hacker could hack into your system. Even 5 years ago, when there was no Stuxnet or no Dooku, I knew what Scada systems were, but we were in no position to write vulnerability signatures to identify vulnerabilities on Scada systems. So I told my boss that, hey boss, we don't have any signatures yet, but we'll start working on it. And I started talking with a lot of people in the industry, with our customers who have some Scada systems. And the more I talked, the more I found out that they are referred to by different people in different ways. Some call them Scada or supervisory control and data acquisition, some call them DCS, ICS, but and there are differences in these different acronyms, but for the purpose of this talk, I'll just refer to all of these systems, industrial control systems, distributed control systems, just as Scada. So I know there are differences, but for this talk, I'm just going to refer to them as Scada. So what really comes to your mind when someone says this term Scada or a Scada system? And I need some audience participation here. What do you think of a Scada system? Examples. Industrial control, that's a good one. Power plant, ooh, that's right here. Yeah, that's right. Sorry? HMI, well, that's good. That's part of the Scada system. So these were some of the systems that came in our minds when we thought about Scada, electrical power lines, windmills, or gas distribution pipelines. So all the systems on top are usually referred as the Scada systems. And generally the rule of thumb is if you sort of hug a Scada system and if you end up hugging an entire city or state or even a country or a continent, that's a good enough indication that it's a Scada system. The systems at the bottom, the systems that are used possibly in food manufacturing, in automobile manufacturing, and so on and so forth, they are generally referred to as industrial control systems. They are pretty huge, but they are not as distributed as the ones on the top, which are Scada systems, which are like really distributed. So okay, there are some differences, but we'll call all of these as Scada for our purpose. So as I was talking with folks from the industry, we noticed that there have been a lot of accidents in Scada systems. And the links here, I'm not sure if they are visible clearly at the back, but they are links from our government, from NERC, to some of the liquid pipeline failures, power failures, and they really find out what was the root cause. So was it operator failure or was it a mechanical failure? And these PDFs, and by the way, at the end of this presentation, I'll give you my Twitter handle where you can get the entire slides and whatnot, so you don't have to write these links. So they outline, they basically give why there were some of these liquid pipeline failures, power failures, etc. So we said, okay, great, there have been some accidents, and in a Scada system, there is always a possibility that there is a loss of life. So that's why maybe our customers want to secure Scada systems. We looked at some cases of vandalisms, and the example here is a pretty famous example from Portland, where some vandals, they destroyed rubber gaskets on power transmission lines. Now, I don't know exactly how you would do that, but they did that. It didn't really cause any power disruption, but the power company had to reroute power. They had to send in crew at a remote location to fix it, and did cause them a lot of trouble and money. So I said, okay, that's why some of our customers, they're requesting these signatures for identifying vulnerabilities in Scada systems. We looked at some of the insider threats, like a disgruntled employee. And the link here is a very famous one. I think most of you must have heard of it. This is from Australia, where an employee was fired from a water treatment plant. And yeah, I see a couple of people nodding their heads. So this is a very famous one. And what does the employee do the very next day? Since he had a good understanding of the system, a blueprint of the system, he knew about the system very well, from the parking lot of the company, he was able to open some of the gates which allowed sewage water, really bad water, into rivers and into the parks. Caused a big embarrassment to the company, and generally it was in the news all over about Australia caused sort of an embarrassment for the country as well. So I said, okay, this is getting pretty serious. But what we didn't realize at that time was what we see now, or what has been termed by the industry as APT. How many of you have heard of an APT? A lot of you, so that's good. APT is Advanced Persistent Threat, and usually it is, the link I have here is not for Stuxnet, it's for Duku worm, which was sort of called as the son of Stuxnet. Everyone heard about Stuxnet and Duku? All right. So in an APT, usually what they refer to in an APT is that the attack usually uses a 0-day, which means that even the vendor or no one really knows about that vulnerability. And also people behind the attack or carrying out the attack, they are not really interested in your credit card information or in your social security number or those things like that. There is usually a bigger organization who wants to disrupt your critical infrastructure, your power lines, your dams, mostly some sort of a big state or a nation. And the link here is actually a pretty nice link. This link is from Symantec. It's not from my company. It's from Symantec. And they did a pretty good reverse engineering on both, on Stuxnet as well as Dooku. And they concluded that the same people who wrote Stuxnet also wrote Dooku. As you know, Stuxnet was the virus or the worm that affected some Siemens PLCs, which would be used in a nuclear power plant. And Dooku was a virus that didn't really do any harm, but was written to collect information. So it didn't send any codes to the PLC, but it just collected information. So we said, okay, this is getting pretty serious, and I guess that's why we have to create these signatures. Usually what happens is when we get such a task of writing vulnerability signatures for detecting vulnerabilities, we get that database or operating system or router or whatever firewall that would be in our lab. We sort of bang on it till it breaks and find vulnerabilities, create signatures for it. Many times there are known vulnerabilities, so we don't even have to do that. We just get that in our lab. We try to exploit the known, already known and public vulnerabilities and just create a signature for it. Pretty straightforward. But as you may recall those pictures of Scada systems, it was impossible to get all these systems in our lab, electrical power plants and whatnot. So what we did was we studied these systems and sort of created a block diagram for our own engineers to understand these systems better. What you have here is on the left-hand side is the field. So these are the components that could be thousands of kilometers, miles away from your right-hand side, which is the control center. So usually the control center is a place where people are manned 24/7. They are monitoring alerts, alarm, and on the left-hand side is the field, which could be, as I said, miles away. So let's take a detailed look at what these different components are. So the components on, or the box which is on the leftmost side is that of data acquisition. So this consists of sensors, meters, field devices, which acquire parameters like light, temperature, pressure, and convert them most probably to an analog signal. Again, not all Scada systems would be like that, not all ICS systems would be like that, but this is a general block diagram that sort of all systems more or less comply with. And the example that I have here is a photo sensor, a pressure sensor, and a temperature sensor. So pretty okay till now. This is just data acquisition where parameters like temperature, pressure, flow, or whatnot get acquired. Now this block has a two-way communication with the next block, which is data conversion. Now this block consists of your PLCs, your IEDs, your RTU, so programmable logic controllers, intelligent electronic devices, and whatnot. And that's what we have here in the pictures. We have a PLC, IED, and RTU. And to give you like a sort of a sense of how big or how small it is, on the right-hand side there is a man holding a PLC in his hand, which is, I guess, about to mount on a, I don't know what that is, could be a wind turbine pole or something. But for all we want to know is on the left-hand side, the leftmost component which we just saw was data acquisition. There is a two-way communication with the next component, which is data conversion, which converts these analog and discrete measurements to digital information. And the third component is communication. So this information is now being communicated to the last block using this communication channel. It could be a wired communication, it could be wireless communication, it could use radio, and most probably it uses one of the 24 or so Scada protocols that are in that table. Now, some people say that there are about 100 different SCADA protocols that exist right now. A lot of open source, closed source, proprietary, non-proprietary. I have not been able to count 100, but I can definitely guarantee that there are at least 24 different SCADA protocols that are being used. So, okay, what we have till now: data gets acquired, data gets converted, data gets communicated, and at the end of the day, it reaches the last block, which is presentation and control. So this is where there are human beings manned, most probably 24/7, into a control station where they monitor alarms, where they react to those alarms. And as you can see an engineer looking at some switches and some displays there. What they are doing basically is they are monitoring alarms. So let's say if your left-hand side has a pressure sensor which senses water pressure, and if the pressure gets high or low, the data gets acquired, translated, and basically at the end of the day reaches this presentation and control layer where operator views this alarm saying that, hey, the pressure is getting low or the pressure is getting high. And the operator can also change the pressure, or you can say, oh, okay, the pressure needs to be this, let me just control this by selecting a knob. Also, this is many times called, as this gentleman said, HMI, or human machine interface. It's just a fancy acronym for what I just described. So these are the 4 sort of building blocks of a basic SCADA system or industrial control system. Let's take a look at where the vulnerabilities are and where an attacker or hacker could hack them. So let's take an example of something between the first and the second block, which is between your sensors and between your PLC. Now this type of an attack, if an attacker was going to attack this sort of component, most probably it requires physical access, because as I mentioned, the left hand side is thousands of miles away. These are sensors. This could be somewhere on a power line, somewhere in Arizona, mounted on maybe an electric pole or windmill or whatever it could be. So if an attacker has to attack that component, usually it requires physical access, and field equipment generally does not contain process knowledge. It contains information like, say, valve 16 or breaker 10B or whatever. But generally without process knowledge, it leads to nuisance disruption. So something that we saw in our earlier example where a couple of vandals, they just vandalized or destroyed rubber gaskets from electrical power lines in this company in Portland. That would be a great example of this type of an attack where an attacker does something, but without process knowledge, it generally causes just nuisance disruption. It's not a targeted attack. It's not an APT. So we said, okay, this is more in the physical world where you literally have to go and physically damage stuff. Let's look at some of the communication threats. So threats which are in this component. So as I mentioned, there are about at least 2 dozen, 3 dozen different SCADA protocols. And if you manipulate those protocols, what an attacker could do is he or she could give a wrong impression to the control center of what is happening in the field. So he or she can manipulate the output from FEP so that the control center get to look at a different picture than what the reality is. So basically change FEP output, which is input to the last component, the human machine interface component. And so we decided to look at a lot of protocol threats which are in these SCADA protocols. First, we decided to look at a protocol called as MODBUS. How many of you know MODBUS? and most probably programmed for Modbus or at some technical level, right? Okay, good. So Modbus is a protocol. It's just like any other protocol that we use, like HTTP or FTP or SMTP. It's just that it's used in industrial control systems. This is, it has a pretty simple client server or master slave organization, and it's pretty much the same. The client requests something from the server gives something back. So it's you can even compare it at a theoretical level to HTTP. I just request something, I get something back. Except that it's a little bit different in the sense the master is usually the client and the slave is the server. Usually in HTTP we refer it in a different way. So these are some of the slides where all the pen testers this morning they said they want to see some real meat. Okay. This is a Modbus frame. It consists of an application data unit and a program data unit. Now, what I'm going to do is I'm going to just dive a little bit into this protocol and how it works and lead this talk. So Modbus is actually a 30 to 40-year-old protocol which was never really intended or never really designed to work on TCP/IP. The way it now works on TCP/IP is just that the TCP and the IP header are just put in front of the entire Modbus header and the Modbus packet. So you have the IP packet, you have the TCP packet, you have the Modbus ADU and the Modbus PDU. So let's get rid of all the TCP/IP headers and all that, and let's just look at Modbus. So all it contains is a header, some function codes, and data. The headers have basically a transaction ID, which is basically, as I mentioned, there is a field equipment here, right? It sends, or let's consider another example where the HMI wants to know what the pressure is, for example. So the HMI would say that, hey, this is transaction number 1, tell me what the pressure is. And the response comes back saying that, hey, the question that you asked, which was in transaction number 1, this is the answer for it, and this is the pressure. So it is just, transaction ID is nothing but a unique question number and a unique answer number. When someone asks you a question, you said, okay, this is question number 1, this is question number 2, and that's what exactly a transaction ID is. Protocol ID is fixed for Modbus. Length is the length of the packet, and unit ID is something interesting, which is basically when the HMI asks this question that, hey, this is question number 1, what is the pressure on unit number 10? And then you get a response back saying that, oh, this is the answer to your question number 1, and this is the pressure on unit number 10. So there can be many units, and that's basically the unit ID is. You can say this is question number 2, now tell me what's the temperature on unit number 100, and so on and so forth. So everyone good here? All right. The function codes are basically, I'm not going to go over the entire table, but these are just what type of requests can be sent. So I can say, hey, this is a read request. Tell me what the temperature is. Tell me what the pressure is. Tell me. Or it could be a write request. It could be multiple reads. It could be multiple writes. So it's just basically instructions on what to do. And this is just a simple Perl implementation of the packet here. So this is the diagram. This is how the packet looks. If you just put that in code, this is how it looks. Basically, you put the 2-byte transaction ID, the protocol ID, length, unit ID, blah, blah, blah. You fill up all what is in the diagram into a Perl packet, and then you send it over a socket. What we see on, if you sniff this packet on Wireshark or any of these sniffers, is exactly what you send. You saw in the red a transaction ID that we chose to be 256. We saw protocol identifier 0, length 6, unit number 1, and this is a request to read some registers. And by the way, we didn't have to modify or write plugins for any of the packet sniffers. So what usually happens is if you are debugging a new protocol or an unknown protocol, the packet sniffers, they cannot sniff the packets because they don't know about that protocol. But most of the packet sniffers, actually I would say all of the packet sniffers, Wireshark or any of them, they already have built-in support for Modbus and a lot of Scada protocols. So if you do this in your environment, you wouldn't have to do anything special. You just sniff the traffic, it will show you clearly what's being sent. So this is just an example request that we saw from this Perl code, and you get an example response that, okay, fine. I got back, I asked question number 256, I got an answer for my question 256. I asked for reading 5 registers, and I got 10 bytes, 2 bytes per register. So I asked some question, what's the status of these 5 registers? I got a response. It could be connected to a pressure sensor, temperature sensor, whatever, I don't know. I just asked the values and I got some values. So everyone pretty good till here? All right, so what's wrong here? There is something terribly, terribly wrong. Okay, that could be it. So something else. That's right, no authentication. So usually any security protocol or any security communication is measured on these 3 sort of holy grail of security: integrity, availability, and confidentiality. And by confidentiality, I mean authentication and authorization. Authentication is, are you authenticated? Do you have access to it? When I sent a request, hey, give me these 5 registers, it just gave me this 5 value for these 5 registers. The protocol or the server never asked me that, hey, who are you though? Are you authenticated to do it? I could have said, write to these 5 registers, which could have meant open or change the pressure or change the temperature. That is a write, basically. When you write to something, it changes parameters. And it would have just done it. There was no authentication. It never asked me who you are. Secondly, no authorization. So even if it had if there is no authentication, there cannot be authorization. Authorization is basically, okay, I agree that you are who you claim who you are, but are you authorized to do it? Are you authorized to do a read as well as write, or just read? So there was no confidentiality. There was very less integrity. So a man-in-the-middle attack could easily be possible. So we said, okay, Modbus was a pretty old protocol, as many of you who raised your hands, you know, maybe 30 years old protocol. And it was not really designed for security in mind. So we will say, okay, we created a signature saying that, okay, if we find Modbus running in your environment or your HMI and your field equipment communicates using Modbus, then we say that, okay, you have a potential vulnerability because the protocol itself doesn't support all these things. So you have to secure your environment using some other securing other things around that protocol, and we'll look at how to do that. So we said, let's take a look at a little bit modern protocol. So we looked at DNP3. How many of you have heard of DNP3? Oh, cool. A lot of people. So DNP3 was developed from the grounds up almost for the electrical grid system in the United States. It is a lot advanced than Modbus, as in Modbus you usually just say, it's mostly based on polling because the client says, okay, give me this, and it has to poll a lot of times. In DNP3 you could have sort of a callback mechanism where you can say that, oh, let me know only if the temperature changes or if the pressure changes or whatever, and then you can get notified automatically. And it has a lot of other improvements on Modbus as well. So, before going to DNP3, so I mentioned about a free tool that I've written. It's a pretty simple tool. It's called Scada Scan, and what it's being used here is you can use it to brute force your Modbus slave IDs. So if you run it with the -m parameter, you could use it to brute force it. I'll again give you the link to it at the end of this presentation, and there is a README online, so it has more on how to use it and whatnot. So this is what DNP3 looks like at in a textbook or in the RFC. It has a user, it has application layer, a pseudo transport layer, and a link layer. And again, we won't go into a lot of details about DNP3, but all you have to know is it has similar things. It has a request part and a response part. You send some request saying, hey, this is a read request, this is a write request, and you get a response. So again, we won't go into this in too much of details. And this is an example from the same Scada Scan tool about DNP3. You just fill in the, or basically create a DNP3 packet. And by the way, this is actual Perl code, so if you just copy paste this and run it in a Perl, it will run. This is the request that we just sent and the response that we received. Our request was basically a link status request to find out what is the status of the link, and we got the status of the link, which is a couple of zeros and ones, each of them meaning something, some link status. Again, we come to the same question: what does DNP3 provide? Now this time it should not be any surprise. It didn't provide any confidentiality, as in you just send a request to change some parameter and it will do it for you. There was some integrity because I saw some CRC here, but not too much. It can easily be hacked. But and okay, this is the Scada Scan tool now running in the DNP3 mode. But all is not lost. So what happened was in 2007, the DNP3 organization came up with a secure version of DNP3, which has cryptography, it had hashing, and a lot of key management, and all the sort of functions that you expect from a modern protocol. So if you have DNP3 in your organization, make sure that it's running the secure version of the DNP3, which is the post-2007 version. So those were some of the communication threads. Any questions, any concerns, or anything that you have seen different to what we have discussed so far? So we said, okay, so there are a lot of threads in Scada communication because most of these protocols were written a long time ago without security in mind. So let's look at let's see what threats or what attacks could happen on the Scada master, on the HMI, or this is the place where usually it's a secured facility with you cannot just go in. There are a lot of guards around, thick walls, whatnot, depending on what HMI it is. If it's a nuclear power plant, there will be a lot of security. If it's just let's say a factory or a water treatment plant, there would be less security. But what you have generally on any HMI is a lot of strong physical security, biometric or retina scans and whatnot to get inside this control room where you usually see, I think I showed you a picture here where there are some monitors and people are manned 24/7 to look at alerts and respond to those alerts. The number one threat that we found to this is that the control system network is connected to the corporate network and sometimes even to the internet. Now, the old school thought was that the control system network should be air-gapped from any other network. So if this is the network which controls your dam, it should be air-gapped. It should not be connected to the network that your HR system uses or to the network that your receptionist use or to check emails and whatnot. But the number one threat that we saw was this control system network is inadvertently connected to the corporate network or to the internet. Can you think of a reason why this could be happening or why such a critical network is connected to the internal corporate network or even to the internet? Alerting notifications. That was the number one reason actually what we saw was that so the control engineers wouldn't have to leave their desk. What happened in one of the instances is that we asked, hey, why is your control network connected to your corporate network, or why do you have internet access from there? And they said, well, these are operators manned 24/7. At 3 o'clock at night, sometimes if they have to check their email or even go online, check their Facebook or something, well, we don't want them to leave, go to their cube and do that. So we just connected that, and I was like, oh, why? In some cases, the control system network is connected to the internet, and that is what I think the other person here said, is there was a company which wanted to give real-time feedback to their customers about, I think it was about power outages and so on and so forth. And all of you in this room know that there are many different secure ways to do that, but the way that they implemented it was to just connect their control system network to the internet, to the web server, which always spews out, okay, there are outages here, 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 and whatnot. Now, as I said, there are a lot other secure ways of doing that, but the way they decided to do it was to connect the control system network directly to the internet. So that's the number one threat. Number two threat is there was no authentication or poor user authentication on these different control system machines. So when you go inside this control room, okay, you have a guard who is with you, or you have some biometric to get in. But after you get in, the HMI, or the place where you go and turn a knob to change the pressure or open a lever or open some damn door, something like that, that doesn't have a poor user authentication. Now, that was okay if the network was not connected to the corporate network or internet, but all the viruses and worms that could jump from the corporate network or the internet, they don't have to get in that control room physically. They can just jump from that network onto the control system network and do the same thing as a human does. So a poor user authentication or just any type of authentication would also go a long way. There were no passwords for these control systems, and well, before I tell you, why would be a reason that there are always no passwords to these control systems which control really important stuff? Why are there no passwords? It's because historically they were air-gapped, there was no need of a password. And also some folks told us that if there is, for example, a fire on the factory floor or something like that, we don't want the operator to try to log in to change something and oops, bad password, oops, try again, bad password, because these are really time critical type of responses, and we don't want to waste time in typing out your password in case of an emergency. Now that sounds like a very logical and a reasonable explanation, but at one of the Scada conferences where people only talk about Scada, there was a person from the U.S. Navy, and he said that he had, I think, 20-year-old young boys and girls typing 25 character long password, which changes every 2 weeks without a single error for like so many years. Now, being in an organization like a military or whatever, you can enforce these things. You cannot really do it in your network or in a private organization. But I think we have to sort of at least start thinking about it, because if they can do it, why can't we? Because these are critical systems at the end of the day, and it's time that we start thinking about them as critical systems. Another thing about that was default passwords. So you have a system from any vendor. I'm not going to mention any Scada vendors in this presentation, but just think about any vendor that you may have. A lot of systems come with a default password. If these passwords are not set, if I'm an attacker, if I'm writing a malware like Stuxnet, what will I do? First thing, I will say, oh, is this a system from XYZ vendor? Yes. What is the second thing I would do? Test if it still has the default password, because the password is already in the manual, it's on the internet, that this XYZ system from XYZ company comes with this default password. So I'll just try that password. So basic things like passwords and default passwords are still an issue when it comes to Scada systems. There is no password change policy either. This is a pretty interesting subject as far as it comes for Scada system, which is basically no patching. A lot of Scada systems that we saw, none of them were patched, unlike your IT systems which are on Windows and whatnot. None of them were patched. Any guess on why that's happening? Are all Scada engineers lazy or something, or what's the reasoning behind it? They don't want to break the system. So no, Scada engineers are not lazy. It's usually what happens is in the 90s, a lot of Scada people who owned Scada system with a lot of proprietary type of Scada system, they asked their vendors that, hey, can you port your HMI or your control systems where there is a human interaction on standard operating systems like Windows or Linux or Solaris? And the vendors just did that. They ported their controls on Windows or Linux and whatnot. And it was great for cost savings because these are normal desktop PCs which are cheap. But all the threats and vulnerabilities and viruses and worms that affect now your normal Windows, Linux, any of your systems now started affecting or will affect Scada systems. And so are patches. So if, for example, your system runs Windows, Microsoft releases a patch every what? Once a month, right? Patch Tuesday, everyone knows about Patch Tuesday. And that means you have to patch your Scada system every month. Now what happens here is you have two vendors here. One is your operating system vendor, which could be Microsoft or Linux or whatever, and one is your Scada software vendor. Now if the Scada software vendor doesn't give you enough guidance that that this patch is safe to apply or this patch is not safe to apply, as a Scada engineer or a person managing that system, what will I do? When Microsoft releases a patch, will I just go and patch the system because I want everything secure? No, my Scada vendor doesn't tell me if the patch is safe or not. So I don't want to break anything. I don't want my stupid patch, I mean not stupid patch, but my patch to break some or stop some conveyor belt or something. So I won't apply that patch. And that basically leads to these systems being unpatched and basically open to all viruses and worms and all sort of malware which could have been stopped if they were just patched. But there is actually no good answer here, and we'll look in a moment when we go on how to secure them, on what could be done. There are a lot of systems which are not even restarted for years, and when we asked them why is your system not restarted in like 5 to 8 years, the simple answer is they say we are not confident it will come back up. And it's, yeah, I had the same reaction, but thankfully I didn't express it. That is the state where a lot of Scada systems are, which is a lot of older operating system, Windows NT, Windows XP, whatnot, which are not patched, which are not even restarted because of lack of support from sometimes vendors and sometimes because the system is just so old that you don't want to shut it down. Since now, as I mentioned, these are operating systems that are off-the-shelf operating systems, your Windows, Linux, and I don't want to just beat up on Windows, I'm just mean any off-the-shelf operating system, Solaris. There are a lot of unnecessary services running. So now you have to do a lot of security management on this system that you would do on a normal IT system. You have to make sure that this system doesn't have, for example, a mail server running just because it came by default like that. And off-the-shelf software, we talked about this already. So just to summarize, some of the challenges that we saw, and the number one challenge which affects Scada systems is the long life cycle of that system. Let's say there is a vulnerability in your phone or in your laptop. You would say, oh, my phone, I'll just get rid of it, I'll buy a new phone. My laptop, maybe in 8 months or a year, I would buy a new laptop. It's cheap. But Scada systems, they are meant to last for decades or multiple decades. And this long life cycle of SCADA system, I think, is the #1 challenge as far as security is concerned. It's extremely expensive and difficult to upgrade even parts of the system. It's not like you can change the entire SCADA system overnight, but even parts of these systems are pretty expensive to upgrade. There is no, as we mentioned earlier, there is no testing or guidance from the SCADA vendors on when to apply operating system patches, and it kind of goes beyond operating system as well, as we'll see soon. There are some SCADA systems which are managed directly by the vendors. So we were at an instance where we went for security. We were being reviewed for security assessment of a system, and we said, oh, it's a standalone, it's a windowed system, we have done thousands of assessments on it. You could just give us the password, we'll do the authenticated assessment. And they said, no, we don't know what the password is because the vendor is managing it. And then the vendor had to be involved and whatnot. So that is one of the challenge as well for auditing these systems. There are now, in a SCADA system, there are a lot of other things on that network. There are data historians, there are web servers. The data historians are typically databases, which could be Oracle, MySQL, and they are also affected by the same thing as an operating system is affected by. Oracle releases patches, MySQL releases patches. What do? Do you apply these patches? Does your SCADA vendor really tell you if it's safe or not to apply this patch? And in more than one cases, we have seen these internal differences between the people trying to secure the SCADA system versus people who own that SCADA system or are responsible to keep it up and running. In many or a lot of instances, what we have seen is someone who is trying to secure that system someday has run a blind port scan or scan using some of the tools on the SCADA network, which caused some of the SCADA PLCs or things like that to go down. And then the SCADA team says that, okay, you guys are never going to scan or do any audits on my system. And that happens more often. So if you are in the team which tries to secure the system, please talk with your SCADA guys first and try to get a window where it's okay if something goes down, because more or less when you scan a SCADA system, something will go down. It used to be a wrong mentality that SCADA is too obscure to be hacked, but I think Stuxnet and Dooku and all these viruses has helped a lot in changing that mentality. So some of the proposals that I have here is do simple things like strategies for password policies, access control for access roles, some strategy for software upgrades and patches, if possible. I know it's very expensive, but try to have a sort of a mini system of your big SCADA system where you can apply patches, where you can test those patches. And having this test environment will go a long way, even though it may cost you considerable amount of money, but it will go a long way. Also demand from your SCADA vendors in contract, in writing, that they will give you guidance on patching, what to do. They will tell you this patch is, they will test those patches first and then tell you on if this patch is safe or not to apply. A lot of times those patch from a OS vendor, you cannot apply that directly on your SCADA system because it's a little bit of a customized system. So what happens is that patch is almost sort of recompiled by your SCADA vendor, and then you get the recompiled patch from them saying that, okay, now apply this patch, because you cannot apply it like the patch from Microsoft directly to your SCADA system. So in that case, have SLAs written down so that they will give you these recompiled patches in a reasonable amount of time. Demand from your SCADA vendors newer protocols, because old protocols, as we saw, they were not really meant for security, and if you are using those, you are just wide open. So demand newer protocols, and also when you get newer protocols, make sure that you are using them. In more than one instances, we have seen that, oh, there is, on the check mark, we have a check mark saying, oh, we have secure DNP3, we have secured this, we have secured that. But when you do an assessment, still the old protocols are being used. So, okay, you bought the new software, but it was never really configured to make use of these new security features. So make sure that's done. And in general apply as Scada systems are now looking more and more like your regular IT systems, regular off-the-shelf operating systems, off-the-shelf databases. Just apply experience from your IT or network management and security experience to Scada. Auditing and scanning will go a long way. For auditing, there are a lot of tools available. There is a free tool that I mentioned. But be very careful because Scada PLCs, sensors and whatnot, they are very low powered devices. A lot of them will just crash or reboot even if they get a ping packet. So if they get something that they don't understand, they will crash. So if you use my tool, there is a big disclaimer here is it will definitely crash something somewhere. It is written with all the care that it should not, but there will always be a PLC or a system which just cannot even handle ping packets or something like that. So if you plan to use either my tool or any other auditing or scanning tool, make sure that you do it in the window. Every factory floor, everyone has at least once in a quarter window for cleaning the machinery or whatnot. So use that time frame to do your initial scan so that if something crashes, okay, it's at least the system is not online. But auditing and scanning can go a long way. So those were some of the proposals that I had. This is a little bit of a roadmap of the Scada Scan tool, which is basically currently in the alpha version. It supports MODBUS, DNP3. In the beta version, what I plan to do is have some Scada master vulnerabilities on it, support for HTTP and SNMP. But in the final version, in the 1.0 version, really what I want is user configurable signatures, because the fact is that no company, me, my company, or no other company will ever be able to get their hands on all type of Scada systems. So if it's a community-based thing where you could upload your own signatures to the tool, that would be fantastic, and that's the goal of the tool. So with that, that's the link to the source code. That's my Twitter handle, and with this, I would like to open up for any questions. I think we may have time only for like maybe 1 or 2 questions. Good. Well, yeah, I mean, there are some custom operating systems available, and as you mentioned, vendors are coming with custom operating systems. It really would depend on the implementation. I mean, if implemented right, you could really implement a real tight Scada system which is not affected by all these vulnerabilities. But on the other hand, Microsoft, Solaris, Linux, these operating systems have been around for decades now. And they have gone through this process and fixed all their bugs and things like that. So I would say it could go either way. Yeah.
One last thing. This starts for the Scada draw. Anybody want to throw one in? We're going to have them draw here. Anybody got one in? Dying to have it. There's one. You got one. All right. It makes them a full scientific here. All right, pull it up. See the back. Oh, this could be our guy here, Alex Morose. Yeah, there we go. Come on, let me over here. We're done. So, if we got like a minute or two yet for another question.
All right, one last question. No? All right. Thank you, folks. Thank you.